Take a look at this bridge. Seems pretty simple, doesn't it? Just a bunch of triangles. But what if I told you that inside this simple-looking frame, there's an invisible war raging, a constant, hidden battle between pushing and pulling forces? It's a huge engineering puzzle, and you know what? We're gonna solve it. Together, piece by piece.
Okay, so this truss is holding up a pretty hefty 1,800-pound load. And to pull that off, some of its parts are being stretched out like a rubber band, while others are getting crushed under the pressure. The crazy part? Just by looking at it, there's no way to tell which part is doing what.
And that right there is the big question, isn't it? We're about to put on our detective hats, our engineering detective hats, and uncover every single one of those hidden forces, one by one.
But hold on. Before we can start solving, every good detective needs a toolkit, right? So let's open ours up and get to know the two main culprits we're looking for, the fundamental forces at play here.
All right, first up we have tension. Think of it as a pulling force, like a rope in a game of tug-of-war. Simple enough. And on the other side you've got compression. That's a squeezing or a crushing force, kind of like when you push down on a spring. Now here's the key. Every single piece of this truss is feeling one of these two forces. It's either being pulled apart or squeezed together.
So, what are the rules of the game? Well, they're called the laws of statics, and honestly, they're our secret weapon. And they're actually pretty straightforward. For this bridge to just sit there and not move, all the forces, up, down, left, right, even the twisting ones, they all have to perfectly cancel each other out. It's all about balance. Everything has to add up to zero.
All right, toolkit's open, rules are set. Where do we even begin? Well, our first move is actually to zoom out. Yeah, before we can see what's happening inside the truss, we've got to figure out the big picture stuff, the forces holding the entire structure up, at its foundations, right there at points A and B.
So to get our first clue, we're going to look at the twisting forces, or as engineers call them, moments. Just picture a seesaw for a second. If we imagine the whole bridge pivoting on point A, that 1,800-pound load is pushing down, trying to make it spin clockwise, right? So to stop it from tipping over, the support over at B has to push up with exactly the right amount of force to create an equal and opposite twist.
And when we do the math to balance those twisting forces, we get our first answer. The upward push at support B is 600 pounds. Exactly. And just like that, boom, the first piece of our puzzle snaps right into place.
Okay, and now that we know that, things get a whole lot easier. Look, we know the bridge isn't flying up into the sky or crashing into the ground, so all the up forces and down forces have to be balanced. We've got a total of 1,800 pounds pushing down, and we just figured out that support B is handling 600 of that pushing up.
So, a little bit of simple math tells us that support A must be doing the real heavy lifting here. It's holding up the other 1,200 pounds. And that makes total sense, right? I mean, just look at it. The big load is way closer to A, so of course it's going to carry more of the weight.
Okay, the big picture is solved. We've got the outside forces nailed down. So now it's time to go internal. We're going to grab our magnifying glass and zoom way in on that first connection point, joint A, to see what's actually going on inside the bones of this thing.
Now, what you're looking at here is a classic tool called a free body diagram. It's just a fancy way of saying we're going to ignore everything else and focus only on the forces acting on this one single point. We know we've got that 1,200-pound push from the support going up, and then we have two mystery forces coming from those two beams, AB and AC.
I know, this looks a little complicated, but trust me, it's just a step-by-step mini puzzle. We know there's a 1,200-pound force pushing up, so to keep things balanced, those two connected beams have to either push or pull back. Our job is to follow the clues and figure out which one's doing what and exactly how hard it's working.
Now, the real key to cracking this joint is a super cool trick involving triangles. You see that diagonal beam AC? It forms a classic 3-4-5 triangle. And this is awesome for us because it means we can easily split its diagonal force into simple up and down and left and right pieces. And since we have to balance that 1,200-pound upward push, we know that the up and down part of AC's force has to be pulling down with an equal 1,200 pounds. So if the vertical part of the force is 1,200 pounds, and we use that handy 3-4-5 ratio to scale it up, we discover that the total force in that diagonal beam AC is a whopping 2,000 pounds. Wow.
Okay, but the big question, is it being crushed or stretched? Well, that force is in tension. Think about it. To stop the joint from flying upwards, that beam has to pull down and away from it. And if it's pulling away, that means the beam itself is being stretched apart.
just like that rubber band we talked about earlier.
But we're not done with joint ages yet. Remember, the left and right forces also have to balance out. We just figured out that the diagonal beam, AC, is pulling the joint to the right. So, to counteract that, the top beam, AB, has to be pushing to the left with an equal force. And our trusty 3-4-5 triangle tells us that force is 1,600 pounds.
And because that beam is pushing into the joint, that means it's in compression. It's being squeezed from both ends. Isn't that just wild? At this one tiny point, you have one beam being pulled apart and another being squeezed together, both working in perfect harmony to keep everything stable.
Okay, that was awesome. We just cracked our first joint. And you know what the best part is? All that hard work makes solving the next one so much easier. Let's slide on over to joint B and track down our final mystery force.
Now check this out. This is where it gets good. We show up at joint B, and we already know 2 of the 3 forces acting on it. We know the support is pushing up with 600 pounds, and we just figured out that beam AB is pushing from the left with 1,600 pounds. There is only one unknown force left to find.
So all we have to do is balance the forces one last time. That last unknown beam, BC, has to do one job: perfectly cancel out the push from the support and the push from beam AB. And when we run the numbers, we find the force is 1,709 pounds. And just by looking at the direction it's pulling, we can tell, yep, this one is also being stretched apart. It's in tension.
And just like that, the puzzle is solved. We did it! By starting with the big picture and then zooming in joint by joint, we have found every single hidden force. It's time to look at the complete blueprint we've uncovered.
So here it is, the final answer key. The top beam is in compression, getting squeezed by 1,600 pounds of force. And at the exact same time, the 2 diagonal beams are in tension, being stretched with literally thousands of pounds of force. We've actually made the invisible visible.
And look, this isn't just some fun mental puzzle. This is the absolute heart of structural engineering. This process is how engineers know, with total confidence, the forces hidden inside every single beam of a skyscraper or a massive bridge. Which leaves us with one last really important question to think about. Now that you know one beam has to resist 1,600 pounds of crushing force, while another has to handle 2,000 pounds of pulling force, what does that tell an engineer about the materials and even the shapes they have to choose for each of those parts?